Morning. In the last class, we have discussed about the Bode plots, and there, when the k is unknown, how you have to plot the Bode plot, and when the k is known, then how you are going to plot the Bode plot. So that is what we have discussed in the previous class. And today we discuss about the module 5, where we need to talk about more on the compensation of control system. So generally all the control systems are designed, whatever we are going to design a control system, it is designed to achieve some specific objectives. Any control system which you are going to design, that is to achieve the some specific objectives. So see, generally we know that some of the requirements of good control system which you have studied in the first module. So it should be it has the less error, means accuracy should be high, and should be speed should be high, means good speed, and the stability, of course, we discussed about, and then damping, means which should not overshoot more, so the damping should be good, damping should be provided. So these are all the some of the requirements which you have studied in the first module. So all the, whatever the control system which you have designed, if we want to have the satisfactory performance, whatever the designed control system should have the satisfactory performance, we need to change, or we need to adjust. If I want to have the satisfactory performance, I need to adjust the system gain k, that is system gain k. So generally in practice, what the adjustment of system gain k will not be sufficient. So what we do in order to improve the performance of this system, why we other than this system gain k, we are going to try to redesign to improve the performance. So what is the problem with only alone with system gain k? Means it improves the steady state response. But there will be a poor transient response when you are trying to adjust the system gain k to have the satisfactory performance. Here it improves the steady state response, that is stability point of view, but it has the poor transient response. So in some cases it leads to instability also. So for in these situations, redesigning of control system is very much required. Redesigning of the entire control system has to be redesigned, so that we can improve the satisfactory performance. So here the design of the control system, we know that it's very difficult to design with accuracy, but these design with the design specifications, when we talk about here, I'm designing a control system, what are the specifications? What are the specifications of design specifications of control system? Is we'll have the different parameters which I have discussed till now. That is some numerical values which are going to give, say for example, a peak overshoot, which you have time domain specifications like peak overshoot. These are all design specifications: peak overshoots and peak time, damping ratio, zeta, and then natural frequency, which is we discussed omega n, and also we can say uh, error coefficients, which you have studied the steady state analysis. During the steady state analysis, we have studied the error coefficients, and also we have studied in the previous classes, that is Bode plot and root locus, all those. In this case, we need to study about the gain margin, and one more is phase margin. So like this, we have the different design specifications which we need to have. So while designing this control system, we need to consider all these numerical values of whatever we have mentioned here. These are all called as design specifications. So it has to be redesigned. It has to be redesigned to meet these specifications, to meet these specifications, set specifications. So the redesigned so as to meet this required specification, we need to in order to meet this redesigning the control system, in order to meet this specification, we need to alter the design or alter the control system. Alteration of control system can be done. Alter the system, we need to alter the system. So here this alteration, we can say alteration can be done. Alteration can be done by using by using some external device, or the alteration which you are going to do in redesigning of the control system to meet the required specification. That system is called as compensation of control system. So how do you define this? Is nothing but when you are trying to redesign so as to meet this requirements of specification, it is very much required to alter this system. It is very much required to alter the system by adding this external device. Such redesign or such alteration, I can say redesign or alteration of the system using this additional device or external device is called as compensation of control system. So this is what we can say what is meant by compensation. Compensation is nothing but it is a redesigning or alteration of the control system using some additional device, that is called as compensation. So here, what are the different types of compensation involved? So what are the different types of compensations? So we know what is compensation. So now we are going to discuss the types of compensations. So what is generally compensation is to redesign, because when the control system is not meeting the specified requirements, it is required to redesign the control systems. So how we are going to redesign or how we are going to alter the system? By using some suitable external device. So that suitable external device we are going to incorporate in the available control system, so that we can improve the performance of the system. So what kind of compensations we have? So there are three types of compensations. One is series compensation. Second one is parallel or feedback compensation. It is called also feedback compensation, parallel or feedback compensation. The third one is combination, that is series parallel compensation. So here, as we told that the external device we can call it as compensator. The name we have given the device name as compensator. So an external device which is compensator, we are going to introduce in the system anyway. Means we have a system control system which has this say G of S, and say this is the feedback system. and I can use this compensator in any of this, in anywhere in this system, in anywhere in this system. So depending on our requirement, or depending on our convenience, or depending on the specifications, the improvement, we are going to add this. So what is series compensation? First we discuss. So series compensation. What is meant by series compensation? So here, the compensator or the external device which is going to be added. See here, the external device which is having the transfer function of this external device is, say, GC of S. So C stands for compensator. So G of S. Okay, so G of S and GC of S. So which you are going to add this compensator is placed in the series with the forward path transfer function. With the forward path transfer function. Say for example, I have a system like this. Okay, so where the forward path transfer function is G of S, and I have the feedback path transfer function is H of S. So it is a negative feedback system. Okay, so this is R of S and this is, say, C of S. And if I'm trying to this add this external device in series with the forward path transfer function, that is GC of S, will be added in series with this. This is what you can call it as this compensator or external device. This compensator is added in series with the forward path transfer function. So the compensator, which is, we can call it as external device, whose transfer function we have given as GC of S, okay, is placed in series with the forward path transfer function of the given system. Then it is called as series compensation system. So this is also called as, this has another name, this is also called as cascade compensation. The flow of signal in this series is from lower energy level to the higher energy level. So the flow of signal from lower energy level to higher energy level, HEL. And here it requires additional amplifiers. In the case of this, additional amplifiers are required in this case to increase the gain. As we told that, to improve the performance of the system, we are going to adjust the gain. So in order to increase the gain in this kind of series compensation system, we require additional amplifiers. And this number of components required in this is more than the parallel scale. So the number of components, other additional components, we can say number of additional components in this case, in order to alter the system, number of components required is greater than the parallel case, greater than the parallel compensation system. So this is about the series compensation system. Now we'll go with what is meant by parallel or feedback compensation system, second one. So second one is parallel or feedback compensation system. Parallel or feedback compensation system. Right. So in this case, the feedback is taken. We know that the feedback is going to take from some internal element. So if I draw here, so we have, say, this one, and I have, say, one is G1, and if I have G2, then this is the internal feedback which you are going to take, that is with the minus h of s. Okay. So in this case, the feedback is taken from some internal element as well as compensator. So here, this is what we can call it as internal element. The bit feedback you are taking from the internal element, and as well as one more element called compensator, that is GC of S. That is GC of S. So here the compensator is act as a feedback element. So here we have this one is called as compensator. This one is called as compensator. Okay. So here, if you look at, one is from the some internal element, and the compensator also we are going to take the feedback. So one is internal element and the compensator. So here in this such a feedback path which are going to provide with the additional internal feedback. So this is the additional internal feedback. So we are providing a feedback path as with the additional internal feedback loop. So such compensation systems are called as parallel compensation system. Parallel compensation system. So when you are providing the feedback which are through compensator, so compensator is introduced in such a way that the feedback path is provided with this additional internal feedback. So that is called as parallel compensation system or feedback compensation system. So here the energy transfer is in the parallel. The energy transfer in this case, it is from high to low energy level. Whereas, hence, in this case, no, compared to this previous series, so because it is high energy to low energy, additional amplifiers is not much required. Additional amplifiers is for to increase the gain or reduce the gain. So additional amplifiers is not required. Is not required because from higher energy to lower energy level. And the number of components, when you look at number of components required compared to this series is very less required in this game. Okay, so this is about the difference between this series compensation and as well as parallel or feedback compensation. So now some of the cases we are going to do combinational compensation system, whereas combinational in the sense combining the series and parallel compensation. So third one is series parallel compensation system. Series parallel compensation system. So in this case, it is we need to provide both the compensation which you have discussed, that is series and as well as parallel. So which we have discussed, both we have to use, both type of compensation we are going to use in this case. So if I draw this kind of, so one is added, that is in the case of series compensator. So I can say this is GC1 of S, which is added in series with the forward path. So here G2 of S. So this is the forward path. Say, okay, G of S or G1 of S or whatever it is, G2 of S. So then we need to. This is one, which is called as this compensator. This device, this external device is added in series with the forward path. So this one is called as series compensation, and one more internal element, which internal feedback element is added to this, so that I'll call it as GC2 of S, which is added as a internal feedback element, So here this one is talks about the series, and adding this internal feedback element, compensator as a internal feedback element, that will talks as a parallel compensation system. So here, depending on the requirement, we add these both type of compensators, that is series and parallel, that is series and parallel compensation. So this is what we can say series. It depends on the nature of the signals which are available in the system, and what are the power levels it required at the various points, and what are the available components we have, and what are the economic considerations which you are going to take. So all this will be taken into the account during the selection of proper compensation. So how do we select the proper compensation? In sense, we have told that is depending on the nature of signals which you have, nature of signals we have, then power levels at the various points, and also available components, which are the available components, and any additional components are required, or economic considerations. If you are looking at the economic point of view also, we need to select based on these points, and also designer's experience. So all these important factors while choosing or while selecting the proper compensation system in the designing of control system, So now we have discussed the what is compensation, why compensation is required, and also what are the different types of compensations. Okay, how we are going to select the compensation system. Now, these compensators or compensating networks, we can say compensators or compensating networks. So, what are the different compensating networks we have? Compensating networks or compensators, we can say, in short, compensators. So generally this compensator which you have discussed the external device, right? Which you have discussed the compensator, which is the external device. External device. What kind of device it is? It may be of electrical network, or it may be of mechanical, or it may be of hydraulic, or it may be of pneumatic, or it may be of combinations of all this. So this compensator which we have talked about, the external device, may be of any of these types, any of these types. It may be of electrical, or it may be of mechanical, it may be of hydraulic, it may be of pneumatic, and it may be of combinational. So here, based on the electrical networks, we are having three types of compensators based on the electrical compensating networks. Based on the electrical compensating networks, we have three types. One is lead network. We have the lead network. Second one is lag network. Then third one is we have lead lag combination. Lag lead or lead lag, we can say lag lead or lead lag compensator. So these are the compensator or network, whatever it is, we can call it as lead network or lead compensator. We can say lead network or lead compensator. We can call it as this one lag compensator also. This one lag lead compensator. So we can give any name, network or compensator, So based on this, these network, okay. Now we are going to study each these networks, that is compensating networks, which is lead network, lag network, and lead lag networks. So when it comes to this, a sinusoidal input is applied. Say for example, a sine wave as an input which is applied to the say above network, it is going to produce a sinusoidal steady state output. A steady state output like this. Okay. having a phase lead with respect to the input, and then the network is called as lead network. If you have the phase, with respect to the input, if you have the network has the lead, phase lead, if you have a phase lead, then it is called as lead network. Lead network. If the steady state output has a phase lag, means there is a lag. If there is a phase lag, means starting, say for example, it is in the uh, starting point, it may be starts from here, okay, or it may be start from here also. This sinusoidal curve is going to start. So there will be a phase lead and phase lag in the so this is called it starts from the some other point. So if there is a lead in the network, so phase lead and phase lag. So in the lag network, both phase lag and both phase lead is also occur in the with different frequency regions, So now we discuss one by one of these networks. So we'll go with first lead compensator. We'll go with discussion on the lead compensator. Right. So as I told that these are electrical networks. So we take one electrical network here, which consists of the resistor 1 and the resistor 2, say R2, and one capacitor is added. Like this. So capacitor is added. Right. So here the current flows with I, and here there is a node point. A node is there. So here the current is going to split into two parts. Say this is I1 and this is say I2. So same I2 is flowing through this. I2 is coming at this point and I1 is coming at this point, and then we are going to get here I1 plus I2, and here as the output means which is passing through this R2 is going to be I. The current passing through this R2 is I, because at this point I1 plus I2, so it is going to come as I. So this is the I'm taking as input voltage, that is EMF, which is EI of t input. Then I'm measuring this output between these two nodes. So if I measure the output voltage, that is we can say E naught of t, and this one. Now, if you take this kind of any is a lead kind of compensating network. This is a lead kind of compensating network. So here, if I want to obtain the transfer function of this electrical network, we have to apply the Kirchhoff current law. So by applying the Kirchhoff current law, we know that I1 plus I2 means some of the currents flowing in the circuit is going to be total current in the circuit. So this I we are going to take into consideration. So if I want to calculate what is the current passing through this capacitor, and current passing through the resistor 1, and the current passing through the resistor 2. So here, if you look at this total current, which you can say C, that is C into through capacitor, we have the equation C into d by dt of difference in the voltage, that is EI minus E naught plus 1 by R1, that is the difference in the voltage EI minus E naught, which is equal to 1 by R2 into E naught, because the output voltage is measured at R2. So this is the input, we can take it as. And then if you take the Laplace transformation on both sides, taking Laplace transformation. So if you take the Laplace transformation in this case on both sides, so this is d by dt. Laplace transformation of d by dt of f of t is equal to f of s by s. So we are going to find out these values here. Okay. So s into c into e I of s, because c is a constant, minus s into c into e naught of s. I'm writing directly. So ei of s minus e plus 1 by r1 is the constant. So ei of s minus 1 by r1 into e naught of s, which is equal to 1 by r2 into e naught of s. So once you take out the input voltages and as well as output voltages on the other side, so take the input voltages in this side ei of s. If I take out the common ei of s from this term and from this term, we have the ei of s. So by taking the common ei of s, we'll be getting s into c plus 1 by r1, then is equal to, we are taking this these two terms, that is this term and as well as this term, to the right hand side, so when you take to that right hand side, I'll be getting and also take out the common e naught of s, we will be getting s into c. This is the first one, and the second one is plus 1 by r1, third one is plus 1 by r2. So now if I want to get the transfer function, so transfer function is nothing but, we have the definition, output Laplace transformation of output response divided by Laplace transformation of input response, that is e naught of s divided by ei of s, which is equal to, so I'll be sending to this side, so I'll be getting s into c plus 1 by r1 divided by, so s into c plus 1 by r1 plus 1 by r2. So this is the thing which you are going to get. So if I take out LCM, if I take the LCM this side, I'll be getting in the numerator, so 1 plus r1 into, I mean s into r1c divided by r1, then denominator I'll be getting s into c into r1 r2 plus r2 plus r1 divided by r1 into r2. So if you cancel out this r1 and this r1, then this r2 will goes up, so I can write this e naught of s divided by ei of s is equal to 1 plus scr1 divided by, I got r1 plus r2 plus r1 r2 sc. Okay. So into, we have got this r2, yes, because this r2 come into the numerator, so into r2. So here if I take out the r1c common, and here s coefficient, whatever the r1 r2c is there, that s coefficients will be taken out, if I get like that, I'll be getting, yeah, so here r1, here already r2 is there, r1c I'm taking, so s plus 1 by r1c I'm going to get, because I'm taking r1 and c as the outside, so already r2 is there in the numerator, so r1 r2 c or r2 r1c will be there in the numerator. Similarly here the coefficient, if you look at this coefficient of s term, r1 r2c, if I take out common, only r1 r2c, So R1, R2, C, if I take out common, so S plus, I'll be getting the term R1 plus R2 by R1, R2, C, R1, R2, C. So this is what we can get. So if I cancel out these terms, these two terms, I'll be getting, so E naught of S, E naught of S divided by EI of S, which is equal to S plus 1 by R1 into C divided by S plus, we can write as R1 plus R2 by R1 R2 into C. So if I replace with the term, say T 1 plus S plus 1 by T, S plus 1 by T divided by S plus 1 by alpha into T. So what I am writing here is this denominator R1 plus R2, which has, that I am taking as 1 R2 by, means I am taking this R1 by R1 plus R2, R1 plus R2, that is S plus R2 R1 into C divided by R1 plus R2. So here this rearranging the terms, so the T which I am taking as T as R1C, T is equal to R1 into C, and alpha I am taking as R2 by R1 plus R2, R2 by R1 plus R2, which is taken as this one. So here, if I take out this as a numerator, which is the transfer function, that is E naught of S, Ei of S, which is a polynomial equation of S and polynomial equation in the S. So P of S by Q of X. If I equate to 0 and if I equate to 0 here, the roots are called as, we know that the roots are called as zeros of the system, and here the roots are called as poles of the system. So if I found the numerator equal to 0, S is equal to minus 1 by T is a pole, and S is equal to minus 1 by alpha T is a 0, in this case. So if I plot this compensating network, it has the pole and 0 at 0 is at minus 1 by T, and pole is at say pole is at minus 1 by alpha T. So this is the plot of given the compensated network, which has the pole and 0, because the numerator is S plus 1 by T, denominator is S plus 1 by alpha T. So here if you look at these both, or we can call it as roots of this equation, S equal to minus 1 by T and S, as having the negative side, so both are lying on the left hand side. It's located on the left hand side. So the pole 0 plot, which you have minimum just value of alpha, generally this alpha will be less than 1 always. Alpha is taken as less than 1, which is R2 by R1 plus R2. So it is always less than 1. It is always less than. Generally it is taken as 0.05. Generally it is taken as 0.05. So what is the maximum lead or angle and as well as alpha? I mean, we are going to get it. So let us see what is the maximum lead angle, maximum lead angle we are going to find out. Lead, I mean, how much is the lead in the network. So in order to find out the maximum lead angle, we have the equation, that is E naught of S is equal to S plus 1 by T divided by S plus 1 by alpha into T. E naught of S by A of S. So we do, say, in replacing the S by J omega, we need to find out the angles, in the sense we need to replace the S by J omega. So what will happen? So E naught of J omega by EI of J omega, which is equal to, S is going to be here J omega. So we can straight away you can take it as Okay, here it you can write alpha into 1 plus ts divided by uh, 1 plus alpha into ts. Okay, so here s is alpha into 1 plus j t omega divided by 1 plus j alpha t omega, alpha t omega. So we know that angles is going to be calculated by using the magnitude of this is going to be calculated E naught of j omega by ei of j omega, which is equal to mod alpha, means alpha is a constant which is taken as, but here alpha into mod of 1 plus j t omega divided by mod of 1 plus j alpha t omega. So if I take this magnitude, so root of 1 plus t square omega square divided by root of 1 square plus alpha square t square omega square, alpha square t square omega square. And the phase angle we are going to calculate by using this. This is the magnitude for the given transfer function. And the phase angle is nothing but numerator angle is, we have the tan inverse of omega t, tan inverse of omega t minus tan inverse of alpha t omega, alpha t omega. So this is the phase angle from the given transfer function. This is the magnitude we are going to get from the. So we can find for which value of this angle pi is going to be, this phase angle is different. For which value of omega, at what value of, at what value of omega this pi is maximum, pi is maximum. So here I'm using the maximum theory, that is d pi by d omega. We are going to differentiate the phase angle pi by using the maximum theory, according to maximum theory, d pi by d omega at omega is equal to, say, omega max, means maximum frequency, will become 0. So we need to differentiate this pi with respect to, so we have the tan inverse x, d by dx of tan inverse x is equal to 1 by 1 plus x square. So d by dx of tan inverse x is equal to 1 by 1 plus x square. So if I apply the d by dt of, tan inverse of omega t minus tan inverse of alpha t omega. So from this I can get, so here the 1 by 1 plus x square, 1 plus x, because with respect to omega, t is the constant, so we can get tan inverse of this and d by dx of omega. So we'll be getting 1 by t by omega square plus 1 by t square. If I take out the x square, 1 by n plus x square, that is 1 by 1 plus omega square t square. So I am going to take the t square outside. So t square outside, if I take out the t square outside, I'm going to get 1 by t by omega square plus 1 by 1 t square. And see, I'll apply this direct. Okay, I'll show you how we can do this. Tan inverse omega t is 1 by 1 plus x square omega square t square minus 1 by 1 plus alpha square t square omega square, right? And here this omega t is nothing but, t is the constant here with respect to omega I am doing. So this will become into t. Similarly here this will become alpha into t. So here if I take out the t square common, I'll be getting, see, 1 by t square into 1 plus omega square, 1 plus omega square into, in the numerator t we have, t. And similarly if I take out the alpha square and t square here common, so I'll be getting alpha t in the numerator divided by 1 by alpha square and t square plus omega square I'm going to get. So now if I cancel out this and this, I'll be getting, so if I take out this t to the numerator, 1 by t divided by omega square plus 1 by t whole square I can take. So minus, similar to this alpha is cancel out. So I'll be taking 1 by alpha t divided by 1 by alpha t whole square plus omega square I'm going to get. So this is the differentiation which I have got and equal to 0 and equal to 0. So this thing is equal to 0 and I'm going to get, so t by 1 plus omega square t square, which is equal to, this equation I'm taking now, uh, which is equal to minus alpha into t by 1 plus alpha square t square omega square equal to 0. If I take out the LCM, I'm going to get t into 1 plus alpha square omega square and t square minus alpha t into 1 plus omega square t square equal to 0. So this is t is common on the both sides, so I'll be cancel out this t. I'll cancel out this t, and I'll be getting 1 plus alpha square. So once again, if I take out the alpha square, alpha square cannot be taken because here we have only alpha. So what we do is we take alpha omega t common, alpha omega t, alpha omega square and t square will be taken common. So then this will become alpha minus 1, then plus we can take it as 1 minus alpha. This is equal to 0. Then from this, omega square alpha into t square is equal to alpha minus 1. If I take out this minus, so it will become alpha minus 1, will be cancelled out, I'll be getting 1. So then omega square is equal to 1 by alpha into t square. So 1 omega, this implies omega is equal to 1 by t, square root of t, and then root alpha. So this will be the maximum frequency at which has the phase lead having the maximum value. Is the frequency at which the phase lead is having the maximum phase angle. So this is the frequency at which we are going to get the phase lead is maximum. So with this, we can find out what is the angle. We can find out by using this. We have the tan inverse of. So we are going to find out tan pi is equal to tan inverse of omega t minus tan inverse of alpha omega t. That is the pi equation which I have got. So tan of a minus b, if I use tan of a minus b use, means assuming this as a, this as a, and assuming this as b. So tan a minus b, we have the equation tan a minus tan b by 1 plus tan a tan b. So if I use this equation, tan a means tan of tan inverse omega t. So I can write tan of tan inverse omega t minus tan of tan inverse of alpha omega t divided by 1 plus tan of tan inverse omega t into tan of tan inverse of alpha omega t. So tan and tan inverse will be cancelled out. Tan and tan inverse will be cancelled out. So in all the terms, I'll be getting omega t minus alpha omega t divided by 1 plus we can get as omega square t square alpha. So we are going to substitute the omega value in the above equation so that tan pi is equal to 1 minus, here omega is equal to 1 by t root alpha, 1 by t root alpha. So straight away I can write the equation as omega t into 1 minus alpha divided by, I can take it as 1 plus omega square t square alpha. So substitute omega is equal to 1 by t root alpha here, so that we'll get the tan pi m. Tan pi m is equal to 1 by t root alpha into 1 minus alpha divided by 1 plus 1 t square into alpha and t square into alpha. So this we are going to get t square will be cancelled out, alpha is cancelled out. So numerator will be getting 2. So 1 minus alpha divided by 1 minus alpha by divided by, we are going to get here into t is there, so tt cancel. 1 minus alpha by here 2, we are going to get 2 root alpha. So here is the alpha is left over, here. So 1 minus alpha by 2 root alpha is the maximum phase angle. So pi m is equal to tan inverse of 1 minus alpha by 2 root alpha is the maximum phase angle. So this is how we need to find out in the case of, this is we have discussed about the lead compensator. So in the next class we'll discuss about the lag compensator. So today we are going to stop here.